3.3. What are we going to do next? We're going to learn the derivatives of all 6 trig functions. Trig derivatives coming up. Okay, so a couple preliminaries. Let's do a super fast recap of just exactly what we need to know from trig and a couple of nuance I want to point out, and then we'll get into what the derivatives of these things are. Okay. Here are the 6 trig functions. I'll just show them all at once here. Okay, so we've got sine x, we've got cos x, and you may have noticed when you took the course that all of the other 4 are based on sine x and cos x. Just kind of the way it works. So we've got tangent x, but of course that's the ratio of sine x to cosine x. We've got cosecant x, but that's the reciprocal of sine x. We've got secant x, but that's the reciprocal of cosine x. And we have cotangent x, that's the reciprocal of tangent x, or you might even think of it as cosine x over sine x. Okay, good recap. Here's a nuance in the notation I want to point out. When it comes to exponents, okay, so when you see, if you see the quantity of sine x or any of the others squared, usually we write this shorthand sine squared x is the way that we say it. So I think that you use that in trig, right? That's not new, but okay, we're definitely going to use that in calculus as well. What would it mean? You know, if the parentheses mean that, then what does this mean, sine x squared? You think, well, maybe it's not written, but it would be implied that there's parentheses there, so it's the sine of x squared, right? And it certainly wouldn't be this. You wouldn't put the parentheses like that. You would, okay. How about a negative 1 as an exponent? Here's kind of this. It's actually an inconsistency in the notation that we just want to be aware of. So if I put the parentheses like so in the negative 1, that would mean the reciprocal of what's inside, right? So that's 1 over sine x, or more easily and commonly thought of as cosecant x, right? Kind of in the same idea as above, what if we just put the negative 1 here? Well, that means it only applies to the x, so that's the sine of 1 over x. Okay, so far everything is consistent. What if we did this? The sine with the negative 1 here, x. And you would think that that should mean the same thing as this, right? I mean, if these are the same, then shouldn't these be this? But they're not. This means the inverse sine of x, right? Or sometimes you call it the arc sine of x. You don't hear that quite as often anymore. You more see this notation and people calling it the inverse sine of x, but yeah, that's the arc sine, right? Okay. Last thing, I didn't write this down, but it occurred to me. In calculus, we always use radians. So if we're ever going to plug a number in for x, we always make sure your calculator is on radian mode. Okay, let's get to it. Here's the big question to start us off. What is the derivative for sine x? Okay. So we're going to do this graphically. We could use the definition of the derivative, right, with the limit, but I think it's more interesting and it really kind of jumps out, and I think it's more impactful when you see it done with the graph. Okay, so I have done a quick sketch of sine x, and of course that's at 1 and negative 1 there, and then we've got 0, pi over 2, pi, 3 pi over 2, 2 pi, and I kind of extended that a little bit in each direction. So also good to remind ourselves of what the graph of sine x looks like, right? It goes through 0, 0, and then it goes up to 1 and back down and does that. Okay. Okay, down here, I have the same xy plane blank, and we're going to do this like graphing the derivative. We'll do it that way. Okay, this is getting exciting. Let's try it out. So, on the original function, we want to look to the points where the tangent line is horizontal. And the way I've drawn it, that happens 3 times. So the slope there is 0, 0 there, 0 there. So when we graph the derivative graph is a graph of the slopes. The y values are the slopes. So here, the slope is 0, so we're going to plot it at 0. The slope is 0, so we're going to plot the y value 0. And the slope is 0, so we're going to plot the y value 0 there. Okay. And then we're going to think, okay, we've got these zeros. How are they connected? Like, does it kind of like go through them this way? Is it curving this way? Is it one of those? Maybe it's something else. Okay, so then we'll look, in between, the points where it's 0. So here, all of these are increasing, right? All of those slopes are going up. Down here, all of these tangent line slopes are negative. So going down, slopes are negative. And then finally, back over here, slopes are positive again. So we know, and then, well, I haven't drawn much there, but those would be negative. So we've got negative, positive, negative, positive. Negative, positive, negative, positive. So it's gonna, kind of wave through them like that. Here's the thing. We don't just want to give a sketch. We want this to be a fairly detailed sketch because we want to know this function, right? We're trying to figure that out. What we need to do, let's look here at this first little, this segment right there for sine, okay? Right there at 0, 0, that is when the slope of the tangent line is the steepest, right in the middle. So it's getting steeper. It's the steepest it ever gets right there, and then it starts to level off again. 0 and 0, it's at its maximum slope right there at the origin. So the question is, what's the slope at that very moment? Because it's going to come up and then go back down, okay? But where is it at 0? Like what, how high up does it get? If we can figure that out, we're really onto something. And it turns out the slope of that line is exactly 1. Okay, it's not clear on a sketch by hand. So what I recommend, graph this in Desmos and then graph y equals x. Okay, so it's passing through the origin, has a slope of 1. Y equals x. And, just visually convince yourself that that's the tangent line. And that's not a proof by any means, but hopefully it'll be convincing if you graph that slope with 1, right? Y equals x, right there. Okay, so that means here, if you believe me, that means right here at 0, the slope is 1. So we graph it at 1. And now let's just think logically what that means. What's the slope going to be here at pi? I mean, because that's another maximum. It's the maximum negative slope because it starts to go down, then starts to level back off. Well, wouldn't it be -1 because it's all symmetrical. So here at pi, we're down here at -1. And then we go, when we get to 2 pi, well, it's repeating itself, of course, so we're back to +1. Okay, let's graph all these dots. So it comes up to 1, comes back down through 0, goes back to pi, comes back here to 3 pi over 2, and does that. Does that graph look familiar? And maybe to some of you, you might have known this a few minutes ago. You could kind of see where this is going. Maybe others of you are like, what is that graph? That is exactly the graph of cosine x. It starts at 1, and then it drops down to pi, and then it goes back up to 1. Oh my gosh. So the derivative of sine x is actually cosine x. Can you believe that? That's pretty cool. Okay. Let's move on. What's the derivative of cosine x? So here's what we'll do. I already have cosine x graphed. So all I'm going to do is set up a new xy plane, and we'll graph the derivative of y equals cosine x. We think of this as like the original, right? Okay, you get it. Now, wouldn't it be crazy if the derivative of cosine x turned out to be sine x, right? If they switch back and forth. They each word, they went the other one. Let's see how this works. We don't want to make any presumptions. If we think of the graph of cosine, let's look at those zeros. So there's a 0 here, a 0 here, a 0 there. So we can plot a 0 at pi, and a 0 at 2 pi. Oh my goodness. Sine does that, right? Sine does this. It goes up, through, down, back, right? Oh man. Okay, well, slow down. Let's keep going. Okay, what would it be here at negative pi over 2? What's the slope there? Well, you might remember, okay, that's 1. So back over here at negative pi over 2, it's up at 1. And then it's 0, and then right there, it's -1. Okay, -1. And then 0, and then +1. So +1. Oh, that's not sine, because sine goes up and then down, but this is doing the opposite. Here's the graph. Let's see. It's dropping down, doing that, doing that, doing that, doing that. Okay, so it turns out it's not sine x like we were all hoping, but it's actually really close. It's the mirror image of sine. Sine would do the very opposite. So it turns out it's negative sine x, the way that worked. Okay, I'm about to we're about to move on to tangent. One thing I want to point out, these, again, we're doing this graphically. This is not a proof or definitive. If we wanted a proof, maybe for sine x, we could go back and use the definition of the derivative, which would be the limit as h approaches 0, sine x plus h minus sine x over h. We could do it this way and arrive at the derivative of sine x being cosine x. We would need some trig identities to help us out with that numerator. I'm not going to do it. I'm not going to talk about it, but it certainly can be done. If you'd like to know how this is done formally, I'm sure Google has an answer, or somebody's got a YouTube on it or something. Okay, we're at 15 minutes. Let's stop this video here. Next up is TangentX.